So we are going to be doing limits today, which is a major part of calculus. In fact, it's what is the backbone of all of calculus. It can give students a little bit of a headache at first, but I think once you get used to it, you're fine. So let's get this started. A lot of people will skip this stuff or not. Nobody skips it, but it deserves a lot more attention than it usually gets. Let me just put it that way. So before we get to the definition of limit, okay, before we get to that, I just want to show you what the idea is here. Okay, so the limit of a function is the y value. So basically the limit of f of x as x approaches some number, and let's just say this is 1 here, 1, is the y value of f of x. There. Okay, so essentially, as you approach 1 from the left and the right, the y value of the function is 0.5. So here, the limit as x approaches, this is how we're going to write it, as x approaches 1 of, and here's the function, x minus 1 over x squared minus 1 is going to be 1. 0.5, sorry, 0.5. You can see that from the graph. So, question might be, it's kind of obvious that it's that, right? I mean, why are we going through all this if it's pretty apparent that at 0.5, I mean, at 1 is 0.5? Well, because what we're going to get to, and this is going to motivate the material a little bit, is exactly what gave us a little bit of grief in the last section, which was the slope of a tangent line. All right, so if you have the slope of a tangent line that you're looking for, remember what we did was we looked at P and Q, and so this was y2 minus y1 over x2 minus x1, where P was the x1, y1, and the Q was x2, y2. I'm motivating why we're looking at limits today, okay, what they're good for. So if you have some function, all right, and you're trying to find the tangent line, let me draw this a little better. Draw something that has a little more curvature to it. And you're looking for the slope of a tangent line here. All right. Remember what you did with Q. Q marched along, and you found the slopes of secant lines as you get there. Well, as x approaches, so let's call this x2, and let's call the x value at P x1. As x2 marches toward x1, okay, they become equal. And when they become equal, they eventually become equal, right? Unless you limit the value of x2. If they're equal, then this here is 0. And so you'll get y2 minus y1 over 0. And this is bad. This makes no sense. So what you have to do is you have to limit what x2 is as you get to x1. If you limit the value of q as it marches towards x1, as it marches towards p, you have to limit the value of q. So you don't really concern yourself a lot of times with what is actually happening at the point. You're concerning yourself with what's happening as you get closer to the point, okay? And the reason is because if those two values are equal, okay, if these two values are equal in the slope formula, then you get 0 and all heck breaks loose. So you don't want that. So what they do to prepare you for things like that, this is coming up. This is going to be known as the derivative. What they're going to do to prepare you for that is give you a whole bunch of functions, and they're going to ask you to find the limit of the limit of the function as x approaches a certain number, okay? So there's two ways you can do this, okay? There's many ways you can do it. So how to find the limit? All right, so we're going to talk about a couple ways at first. Okay, one thing is to graph it, graph f of x. Another way is to plot points as q goes to p. All right. So in this case, p will be the value here. P is going to be this guy right there, p. All right. So what we could do that for this problem here. All right. x1 minus 1 over x squared minus 1. So what we could do is, for example, we could say find limit. All right. So you can pick values on both sides of 1. All right. 1. All right. So, for example, let me get a thinner pencil. You pick x, and then, well, you know what? They do it horizontally in the book. So x, and I'm going to call this all of this. I'm going to call this y. This is y. So you could start. So we're approaching 1, right? So let's say that 1 is like right here. 1 is right here. So I'm going to approach from the left and the right. So a little more than 1 would be like 1.001, and then 1.01, 1.1, all right, and then maybe 2. And then on the other side, you could do 0.999, and then 0.99, and on and on, okay? And when you plug these values in, you plug all these values in for x in both the top and the bottom here, you're going to get some numbers, okay? So what I'm going to do is I'm going to go ahead and do this. I'm going to pause the recording. I'm going to plug in all these numbers. All right, so that's what I've done. So what we have here is underneath, all these guys are here, all these right here. These are the values of the function on either side of 1. So on either side of 1. So the limit is as x is approaching 1 here. Okay, we're determining that by picking values on either side of 1. So what I did was I picked values a little bigger than 1. Okay, so right here. And then values a little smaller than 1. And what I got values that approached 5 on either side. Okay, they approached 5 on either side. So it looks like our answer is probably going to be 5. All right, and indeed it is. We're going to see that in the next section. All right. So basically, this is what you do, unless you know how to graph the function. We could have just graphed this function and kind of estimated it. Now, there's a danger in that though, because a lot of times the graph isn't very easy to get to. All right. Now, here's the thing. I want you to compare. Let's compare these two problems here. So we have f of x is x minus 1 over x squared minus 1, and the g of x is a piecewise defined function. And if you notice, they're exactly the same, except at 1. Now keep in mind, we couldn't have plugged in 1 over here anyway, right? Because you get 0 in the bottom. You get 0 over 0 actually. In the next section, we're going to learn how to deal with that. But for now, this is what we got to do. If you notice, this function right here is the same as this function. And so, except at the value of 1 itself, all right, at the value of 1 itself, they're going to assign the value of the function 2. Now, the limit is still going to be what we found before, which was, I'm sorry, this was 0.5, not 5, 0.5. We're still going to get 0.5 because if you look at these two graphs, the value, the graphs of f of x and g of x are the same, except at this one point at x equals 1. So if you look at the graphs, let's look at them. The top function, f of x, okay, there's a hole here because you can't plug in 1. But in the bottom function, there is a hole, but the value of the function is at 2, right? They assigned it 2. Right here, see, 2. Now, the limit as x approaches 1 from either side is still 0.5. It's still 0.5 because you're not really concerned with what's happening exactly at 1 itself. You're concerned only what's happening around it, so around 1. So it doesn't matter that the value of the function g, this is g of x, is 2 at 1. See here, so g of 1 is equal to 2. It doesn't matter that the value is 2 there. The limit is still 1. 0.5, sorry, 0.5. So here, what we have is the limit as x goes to 1 of g of x is equal to 0.5 still, okay? Not 2. And this is where a lot of people will get confused. All right, so there's problems in the book like that. I'll let you work through them. All right, now, it's kind of dangerous to sometimes work with just plugging in numbers. And this is a good example of it. Tangent x minus x over x cubed, limit as x goes to 0. So let's look at that for a second. Let's pull this over. So we're going to look at limit as x goes to 0 of tangent x minus x over x cubed. So if you plug in 0, you're going to get tangent of 0 minus 0 over 0 cubed, which is just 0, because tangent of 0 is 0. 0 over 0. And so you don't know what this is, right? By the way, in Cal 2, we're going to deal with this a little. In Cal 2, you deal with this in a better way, than in a different way. But for now, this is all we got. So what you can do here, you can't factor it. You can't play around with this, or you can't do anything with this. Certainly, you can't pull out an x or anything like that. Nothing you can do here. You can't cancel these. Don't even do that. Please don't, because it's not right. So what you can do though is you can graph it, kind of see what it looks like graphically. All right. So what I'm going to do is I'm going to pull over a Wolfram Alpha. We're going to plot this puppy. All right. And I've already plotted it here. Now what I want to do is I want to make it go from less to less here. So let's just see what happens. You just graph it straight out. And this is what it looks like. Now this is from -2 to 2. Okay, so apparently as x is going to 0, that's what we're concerned with. X is going to 0. The value kind of looks like it's going to be 1, 0.3 maybe. But if you look from -12 to 12, you don't know what it is. So you got to zoom in. So you zoom in, and you're like, well, I don't really know what that is. So maybe you zoom in a little more. So what I'm going to do is I'm going to say from -0.1 to 0.1. Let's see what that is. And it's going to graph it. Ah, here we go. So it looks like it's about 0.3 something. All right, 0.3 something. Now, what if you go further in? So maybe 0.001 to 0.01. Negative. From -0.001 to 0.001. Let's see what that looks like. All right, it's computing it. Takes a little while. Now, see, there's issues here. See, now what's happening here is the computer doesn't know what to do with it. It's the values getting closer and closer to 0 on top and the bottom. The computer it can't handle this very well. So then you end up with gibberish here. But the answer is actually 0.3 repeating. Okay, so you have to be careful with this. It's not this at all. okay, it actually is 0.3 repeating, okay? And there's ways to do this, like I said, in Cal 2, all right, Cal 2, that's going to help us out with this kind of problem. Now, while we're at it, what I want to do is I want to look at this guy right here, all right, sine x over x, all right? So if you plug in values into a calculator within tens to the -7, so what I want you to do is I want you to try this on your own. It's a nice test problem. X versus y, where this we're going to call this y. You can plug in like, so we're looking at 0. So let's march to 0 from the right. Let's say it's 0.9, and then 0.5, and then 0.3, 0.01, things like that. 0.001. All right, and then when you plug these values into the sine x over x, let's see what you get. I'm going to go ahead and pause the recording. I'm going to plug these in. So what I've done is I've done that, and it looks like as you plug in values very close to 1, very close to 0, see the limit's going to 0, as I plug in those values, so I plugged in 0.9, I got 0.87. Plug in 0.5, I got 0.96. I plugged in 0.3. Now see, I'm plugging it into sine x, and then I plug it into x. I get 0.985, and as I keep going, all right, I get something really close to 1, okay? And so it appears that the limit of sine x over x is equal to 1. So it looks like the limit as x goes to 0 of sine x over x is equal to 1, and it actually is, okay? So it checks out. But this is real tedious, you know? I mean, like, who wants to do all this? I mean, you do it a little bit in the beginning of calculus, and then it's like, okay, I'm done with all this. But, you know, a lot of times this is what happens, you know? So, anyway, so then you get something like this here. Now, before we go on, let me show you something about sine x over x. If you plug in 0, you're going to get 0 over 0 again, right? So if you just plug in 0 right away, you run into problems immediately, okay? The sine of 0 over 0, well, the sine of 0 is 0, so you get 0 over 0. And then you don't know what this is. It could be anything. In actuality, if you look in the previous problem, we got 0 over 0, and that one was, that answer was 0.3 repeating. Okay? Now we get 0 over 0, and the answer was 1. So I'm not saying that 0 over 0 makes any sense. I'm just saying that it's not a number. This is not a number, okay? I'm just saying that if your function values approach 0 over 0, you don't know what it is. It's not 0, it's not infinity. It could be any number you want. Not any number you want, but it could come out to be any number. All right, so now let's look at this one, sine of pi x over x. Now what I want you to do in your own time is I want you to go back to Wolfram Alpha and graph this, and do it from different numbers to different numbers. So the website I was just using to graph was www.wolframalpha.com. So go check that out and do some graphing with that. And what I want you to do is I want you to plot it. So you'll do plot, and then you write your function in here, and then do like from 0 to 10. And then from 0 to 0.1, 0 to 0.001. And you'll see that it's just absolute gibberish in the middle here. So finding the limit here is impossible, okay? I don't know what it is. It's not impossible, but you can't do it using the method that we're showing you here. So finding limits is pretty simple whenever you have a graph, okay? A nice little graph. Finding the limit wasn't that bad here. But then not always is it very easy. So you just got to be careful. And keep in mind, I'm doing some of the harder problems. So let's go back up to this definition, the limit of a function. And let's talk about it for a second. Intuitive definition of limit. So let's walk through it. Let's see. Let's try orange. Suppose f of x is defined when x is near the number a. So what you have here is you have your function. All right, you have some function right, like this. And then you have an a value. And your function is this orange one, f of x. So let's see, suppose f of x is defined when x is near a number a. Yeah, it's defined because the graph exists there, sure. This means that f is defined on some open interval that contains a except possibly an a itself. So there's an open interval, open meaning that you're not including the values on the endpoint, okay? Then we write the limit as x goes to a of f of x equals L. So what's going to happen at a apparently is the value of f, the limit, remember it's always the y value. The limit is the y value. I wish they had told me that when I took Cal 1. It's the y value that exists there, okay? So here's your y value. So the limit as x goes to a of f of x is L. And if we can make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a. All right, we're going to get to this concept a little later in 2.4, but the idea is that in a little interval around a, okay, a little interval around a, you can get closer and closer to a without actually getting to a, and your value here is going to be L. Your value of your function is going to be L. Now, this could be some open dot here. F of x doesn't have to exist at a, but the limiting value will still be L, okay? All right, so that's the definition. Now let's look at some other problems. All right, so you have one-sided limits. I'm going to let you do this on your own. Look at one-sided limits. It's just limits from the left and the right, okay? So what you want to do is just look at the examples there. And what it says basically here is if you're coming in from the left and the right, let me just look at this function here. And let's suppose that this is your a here. This is a. So if you're coming in from the left, from the right and then the left, okay, and the limit value is the same from both sides. So suppose this is my L. If the limit value is the same coming in from both sides, okay, so the limit values are going to be here on the y-axis. Remember, the limit is the y value. So if the limiting values are the same coming in from both sides of the graph, which means above L and below L, if they're the same and they're both L, then the limit exists, okay? So that's what it says here. Let's just go back to it. It says, the limit as x goes to a is L, that's the y value, if and only if, so this goes both ways, this way, left to right and right to left, if the limit coming in from the left, so coming in from the left, we say x is going to a from the negative side. And then coming in from the right, x is going to a from the positive side, okay? A may be positive or negative. It's just saying that, you know, the negative side of the number line, okay? If these are both L, okay, if you're coming in to a from the positive side and then the negative side, and that value is L on both sides, then the limit is L, okay? It has to be, all right? This is really important. And then you have, these are called one-sided limits, okay? So let's do a couple of these. So let's try A and B. So let's try A. So as t goes to 0 from the left, so this red graph is g of x. Okay, I need purple. Here's purple. Purple. So g of x, oh, cool, is this function. So let's see what's happening as t is going to 0 from the left. So as t is going to 0 from the left. So apparently this is the t-axis, and then this is the g-axis here. All right. So as we come in from the left, all right. So let's march in using blue. to 0. All right, so 0 is right here. The value of the function is -1. So this right here, this is -1. As we come in from the right, so this will be, so here's how we write it. We write the limit as t goes to 0 from the left of g of x, I'm sorry, it's g of t. G of t is going to be -1. Okay, now part B says, let's have t go in from the right. So now we come in from the right. Let me just do this in a different color. Let's say green. So as we go to 0 from the right, it looks like, see, I'm not going to close in the dot. Can't close it in. But it looks like it's going to be at -2 instead. So limit as t goes to 0 from the right of g of t is -2. And so since these two aren't the same, all right, these are not equal, that means that the limit does not exist. Now, the limit on each side exists, but the limit of g of t at 0 does not exist as t goes to 0 of g of t. We'll say d and e does not exist. Does not exist. Okay? So it does not exist. And so we'll just write d and e. And this is what WebAssign wants too. All right? Now let's do a couple more of these. Oh, let me just do one more or something. So let me erase all this. What's a good one here? Let's see, this is 2. This is at 1, this is at 2. All right, so this is 2 here. Let's look at that one. All right, so let me erase all this. So let's look at the limit as x goes to 2 from both sides. All right, so I'm going to pick blue coming in from the left. So the limit as t goes to 2 from the left of g of t is, okay, so you look at the y value, and it looks like it's going to be 2. So the y value coming in from the left, is going to be 2. And then now coming in from the right, we'll use green again, coming in from the right, looks like it's on the x-axis itself. If your y value is on the x-axis, y is 0 there, so the limit, remember, if you're on the x-axis, the y value is 0, so the limit as t goes to 2 from the right of g of t is 0, okay? And so once again, the limit doesn't exist there. Normally, if there's a break in the graph, and you have to lift, if you have to lift your finger, lift your pencil off the graph ever to keep going, the limit won't exist, okay? It just depends. If it's a point, though, it's just at a point, that's different. All right. So here the limit as t goes to 2, g of t does not exist. Okay. Again, now what is the value of g at 2? The value of g at 2 is 1. That's this point right here. This is at 1. Okay. Doesn't matter. It doesn't matter that g is defined at 2. We're looking at the limit. The limit doesn't exist. Okay. All right. So now let's talk about the an infinite limit. So what's going on when f of x goes off to infinity as x goes to a? That's these graphs right here. So if this is a here, let me get a different pen. Let's use this one. If this is a here, then the value of the function is going off to infinity. Okay? What's going on with this pen? Pick that one. The value of the function is going off to infinity. That's bizarre. So what we say is that the limit, oh I know, that's what the problem is. We say the limit of f of x, as x is going to a, is infinity. Okay? And it could be negative infinity too. Negative infinity here. So here's the limit. This is a of f of x. Let me draw this a little better. Limit of f of x as x is going to a. We say that's negative infinity. Okay. We're going to be making this a little more precise later on. So these can be a little difficult because you got to plug in a bunch of numbers. So like this one, you got to plug in a bunch of numbers. Right here, what you would probably do is plug in a bunch of numbers on the left and the right of 1. So you would have to do x versus y. And you could say, okay, maybe 1 is right here. So we're not allowed to plug in 1. Because if you plug in 1, you're going to get 0. You get 0 on the bottom, which is bad. So, I guess what you could do is plug in 1.01, 001, and 1.01, 1.1, and you can plug that into the function, and then on the other side you can do 0.9, 99, 0.9, 9.9, and you can see what you get. Actually, I like doing it vertically better. So I'll tell you what, I'm going to pause the recording and I'll plug all these numbers in. Alright, so that's what I did, and it's apparent that this number is huge. As we go to 1 from the left, from the left, remember these are numbers, here's 1, and then 0.99s are charging towards 1, and then on the other side of 1 we got 1.001, all these 001 guys. So coming in from the left, this is right usually, coming in from the left, we're going to get huge numbers, and coming in from the right, we're going to get big numbers as well. And so it looks like at 1 it's going to be infinity, and it is. Now you can verify this by graphing it. Okay, so what I'm going to do is I'm going to pull in Wolfram Alpha here to help us out, and I'll show you that the graph verifies this for us. Now what I've done is I've plotted it from 0 to 2, just from 0 to 2. And it's apparent that at 1 there's like an asymptote going off to infinity on both sides. If you're not careful, if you take out the from 0 to 2 piece, then when you graph it, it's not going to be as user friendly. So you have to see. You don't know what it is here. It could be anything. So it's not as user friendly. So just use that feature. You can actually make it even more, you can make it even closer. You could make it from 0.9 to 1.1 and see what that is. And it might even be better. Let's see. It's about the same. So there you have it. So let's move on to another problem. So these are tedious. Hey, nobody wants to do these. But I'm not going to give you a whole lot of these to plug in, all right? But I want you to just get your hands dirty with it. This is a problem that I'd like to see maybe on a test, natural log of sine x. But this, who wants to plug all this mess in? So anyway, so it turns out that vertical asymptotes from algebra come into play here big time. Because if the limit is infinity or negative infinity, then you have a vertical asymptote there, okay? So I want you to read over this, okay? Read this, okay? Because I'll be asking you to find the vertical asymptotes. So to find the vertical asymptotes of this function, okay, normally in algebra what you do is you say, well, where is the denominator equal to 0, okay? And if it is, then that's the asymptote. So if the denominator is equal to 0 at 1, let's say, then the vertical asymptote is 1. X equals 1. So let me see. Let me say if denominator says at x at 1, then the vertical asymptote is 1. All right. But in calculus, what I want you to do, I don't want you to do this business here. I want you to go ahead and find the limit. So in a calculus way, what you would do instead is you'd say, okay, find the limit as x approaches. Wait, time out. No, you can't, because we need the actual number. Yeah. So I guess what you need to do is find out what the vertical asymptote and verify. Yeah, here we go. Verify that the limit of f of x as x goes to 1 is infinity. Okay. Now, I'm not talking about this function here. Okay, this function here, I don't know what the vertical asymptote is. You'd have to set the denominator equal to 0. It's not hard. I'm just talking about in general. Okay, and that's what you got. That's the lecture. I like this problem a lot. So in the Q&A, I invite you to ask about it. Look at it first. Okay, so read this problem. All right, so that's a nice little intro to limits. Okay, if you have any questions, just email me. It's not a problem at all.